Okay, so 5.2 is all about exponential functions and graphs. If you remember, 5.1 was the inverse functions, and it's going to become more apparent once we do 5.3 why we start with inverse functions before we talk about the exponential functions in the rest of chapter 5. So exponential functions are functions with equations that contain a variable in the exponent itself. And so it's important that you have that in your mind when you're looking at different functions to determine, is it an exponential or is it not? For the exponential functions, we have a base that we usually call b when we're talking about general notation. So the base is the b, and then our exponent is the x. It kind of makes sense. Bases start with b, exponent sounds like it starts with x. Where b is a positive constant other than 1, and x is a real number. Now, as we progress through this, we're going to see negative bases, but it's not really b that's negative, because you're not going to see something that looks like this. That has a negative b as a base. You can't have that. But you can have situations like this, because this ties back to 2.5 with our transformations of functions. This negative out front simply tells us that we are going to be reflecting over the x-axis. So these are different. This one we cannot do, this one we can. Because what this is it's a negative 1 times a b to the x. So just kind of pointing that out before we dive into the graphing side of this. I went ahead and made a table to kind of show different exponential functions, talk about their bases, and then also show you some examples of things that are not exponential functions. So I'm not going to go through the whole list. These are pretty self-explanatory. The number on the bottom is always the base, and so you have lots of different examples here. The reason why I like having this table is because it shows you that in your exponent you can have just the variable itself, or you can have a variable plus or minus something. You can also have negative variables up there and things like that. So just note that it's not just the variable itself that can be in the exponential spot. Now, the other side of our table are things that are not exponentials, and I give you a reason why. So for the f of x function, this is our quadratic, so hopefully immediately you would have noticed that that's not an exponential function, and that's because the variable's in the base. Can't have it. G of x is not not an exponential function because the base is 1, and we can't have the base equal to 1. Same thing for h of x. It doesn't obey the rule that b has to be positive. And then the last one is because we, again, have a variable in the base. Yes, we have a variable in the exponent as well, but if we have a variable in the base, then it's no longer an exponential function. So all of yours will look like the left side of this table. And we're going to start by graphing a couple, just so that we can see what's going to happen with these exponential functions. And the way that we start graphing any type of function when we don't know what it's going to do is we use the point plotting system. So we're going to make a table. We're going to plot some points. I will warn you, exponential functions, they grow really fast or they shrink really fast. Whenever you think about business, you want to see exponential growth in your business. You want to see exponential growth in your profit margins and things like that. So these will get very big very quickly. So when you pick your x values, pick small ones. Because if not, you're going to be making a ton of little tick marks on your paper and pencil at least. Obviously in Pearson it's a little bit different. So I'm going to pick and do 5, just so that we have a really good example of what's going on. I'm going to do 2 negatives, 0, 2 positives. Really, after the first time you see these, you can do 3. 3 is a good one. And then for you live in class, if you want me to, at the end, I can show you how this works in Pearson, because Pearson's a bit different. It's not like plotting a line where you actually plot the individual points. They have like a system set up that you kind of fill in the missing pieces. And I can show you how it works on Pearson. All right, so let's do -2, -1, 0, 1, and 2. Well, this would be 2 to the -2. So we're going to have to remember what happens with negative exponents. Does anybody remember? Negative exponents. Well, if you have b to the negative a, then what ends up happening is it goes to the denominator, that's a b, with a positive a. So 2 to the negative second power becomes 1 over 2 squared, which is 1/4. So when x is negative 2, we're at 1/4. So when x is at negative 1, we're at 1/2. What happens when we have 0 as our exponent? It's always equal to 1. That's right. No matter what that base is. Anything raised to the 0th power is 1. So we're going to be here at 1. That one's a little bit high, it looks like. Then we'll be at 2 to the first power is 2. 2 squared is 4. 2 to the third power would be 8. So hopefully you see that it's going to grow quite quickly. And then before I finish off the left side of this swoop thing that I've got going on, just thinking about logically what happens whenever, I have -1, -2, -3, -10, and so on and so forth. Is there a way for me to get a negative y output in this case? Or even 0? Is there a way for me to raise 2 to the somethingth power and get 0? No, there's not. So as we will see here in a minute when we flip over, there's actually an asymptote that runs along our x-axis here that our graph will hug as it comes down. But this is an exponentially growing graph. So when your base is greater than 1, this is what your graph will look like. Always. It's going to swoop up. If you're in business, this is what you want to see. So let's look what happens whenever we have a base that's less than 1. Notice our base is still positive, but it is less than 1. It's a fraction. So again, I'm going to do 5 points just to kind of really showcase what's happening. I'll do -2, -1, 0, 1, and 2. This time our base is 1/2. So 1/2 to the -2 power. Well, up here, it turned a whole number into a fraction. Down here, it does the opposite. It flips it. So instead of 1 over 2, I now have 2 over 1, and that's being squared, so that's 4. Fractions raised to negative exponents become larger numbers. So at -2, I'm at +4. So 1/2 to the -1 would be the same thing as 2 to the first power, which is 2. 1/2 to the 0th power, anything to the 0th power is 1. Then we have 1/2 to the first power, which is 1/2. 1/2 squared is 1. Basically, you can think of it 1 squared over 2 squared if you want. It's 1/4. So notice that when our bases are fractions, we still get the same general swoop action happening. But instead of rising to the right, like we had with our base equal to 2, we now are falling as we go from left to right. This is definitely not what you want to see whenever you're doing a business at all. This is exponential decay is what we would call it. And everything starts plummeting really, really bad. And we're getting really close to 0. Are there any questions or comments on those? All right, let's flip over. The whole back side of this front page is just for reference. This is one of the reasons why I decided to make a handout, because before, y'all would have to write all this stuff down, and then I just stand up here in silence for about 20 minutes, and that's fun. So these are characteristics of your exponential functions, just general function, with absolutely no transformations. Nothing moved. And I mentioned that because it says, unless the graph is shifted, unless the graph is shifted, unless. Because if we start doing transformations like we did back in 2.5, then some of this gets moved around. But when we're talking about a general basic exponential function like 2 to the x or 1/2 to the x and things like that, all of these things hold true. So the domain of our exponential function is always negative infinity to positive infinity. Everything gets covered. The range will always be 0 to infinity unless the graph is shifted. That's because we actually have an asymptote here that lives along our x-axis. So, I mean, if we end up shifting the graph up 1, then your range will move up 1. If we shift the graph down 3, your range moves down 3. So it's pretty, like, it makes sense what happens to our range. It's affected by the vertical shift. And if you want to put that as a note over there, you totally can. Affected by vertical shifts. You don't have to. It's whatever you want. Your y-intercept is always at 0, 1. Again, that's unless we have some shifting going on. And this shifting could be vertical shifting or horizontal shifting. Those will both affect your y-intercept. But this comes from the fact that anything raised to the 0th power is 1. That's why we always cross there. We cross there on both of our graphs. This one was x to the, 2 to the x, and this one was 1/2 to the x, but both of them crossed at that 0, 1 spot. There's no x-intercept. Again, we have an asymptote there, so we're not going to cross it unless we shift our graph. If our base is positive, then we have what's known as an increasing graph, or a growth, an exponential growth situation happening here. And the larger the b is, the steeper that increase. So we did it with just 2. If we had base 5, 5 to the 2nd power is 25, so it grows way faster. It just depends on how big that base is. If we live in our fraction range here, between 0 and 1, then we have exponential decay, or a decrease in our graph. And the smaller the value of our b, the steeper the decrease. Now, in 5.1, we talked about inverse functions, and to have an inverse function, you had to be 1-to-1. Exponential functions are 1-to-1. They pass both the vertical and horizontal line test, so they have inverses. And we will see in 5.3 what those inverses are. And then the last point is that they have an asymptote at y equals 0 unless we have a graph shift. And then underneath the very general pictures that I have here, where b is greater than 1, or you have your fractional b, we have the table from 2.5. Actually, it's not from 2.5. It's from this section, but it's all the same transformations. I did pick this one up out of this actual section because this one is applying a general understanding here of our exponential functions. So we still have horizontal shifts, we still have vertical shifts, we have the reflections over the x-axis and the y-axis. We also have horizontal stretching and shrinking and vertical stretching and shrinking. I will say I went through your homework and we don't have any stretching and shrinking action going on. We kept it a little bit simpler, and so we deal with the top half of this. It's still good to have that information and to be able to use it, but all the problems that we encounter are going to stick with vertical and horizontal shifts, reflections over the different axes. And so what's nice about this, and why I liked how they gave an actual example using the exponentials, is when you are reflecting over the x-axis, that happens with a negative out front. But when you reflect over the y-axis, that happens with a negative in your exponential spot. And so you're going to have this happen in your homework, and you're going to have to be able to apply this and actually use your graphs to do this. So if you didn't master the transformations back in 2.5 when we were dealing with our absolutes and our quadratics and things, here's another opportunity to do it. And what's nice about it is this will hopefully refreshen all that right here as we're getting ready to go into the final exams in a couple of weeks. So all of these are the exact same transformations that we had in 2.5. They all obey the exact same rules. Nothing is different. It's just now our base function is our exponential function. Are there any questions or clarifications on any of the facts or anything like that? All right. So let's do one more that has some transformations, and then I'm going to talk to you about base E for like half a second. And then I can show you on Pearson, if you would like, how this kind of works. All right, so this one's got a little bit more going on than the other ones that we did. We have 3 to the 2 minus x plus 3. So definitely some stuff going on here. I would honestly probably rewrite this and then make some notes about what transformations are happening. Because again, if I know what the base function looks like, or the mother function, which I do, that was on the last page, and then I know what transformations are happening, then I can know what's going on with my graph. And it makes it easier. Now, we're still going to do point plotting to actually get the points for the paper pencil, but then I'm going to talk to you about how you would do this one on Pearson and make it a little bit easier. Okay, so I would probably choose to rewrite this top part. And the reason why is because I have a 2 minus x. And I don't really like it written that way because on my table, on the previous page, anytime we have an exponent in here, I like to keep it written first. And then write my horizontal shift right after it. That way I don't get confused what these numbers are doing. So this is just a personal preference. You don't have to rewrite it. But I would probably rewrite it as f of x equals 3 to the negative x plus 2, and then I have this plus 3 out here. Just so I can really hone in on what's going on within this. What does the negative mean? What does the 2 mean? What does the 3 mean? What does all this mean? And so I'm going to make some notes. What does this plus 3 out here tell me? Let's start there. That one's usually the easiest one. Thinking back to 2.5, if we put plus or minus a number outside of our function, what did that affect? That's our vertical shift. Yeah, and vertical shifts always go in the direction you would think. So this is going to shift everything up 3 units. Now, when we had plus or minus within our function, that was our horizontal shift, and it went in the opposite direction. So this plus 2 tells me what? Like, which direction am I going to head? I'm going to head to the left 2 units. And then I have this negative out front, which tells me what? Yep. Reflects over y-axis. So we've got a lot of things going on. My base is a positive 3, so that means it would look like an increasing graph. It's going to look like a nice little swoosh. But I'm shifting it up 3 units, I'm shifting it to the left 2 units, and then I'm also flipping it so that it reflects over the y, which is not that way, which is this way. So we got a lot of stuff going on. So that's why I like to do the plotting by points when we're doing with lots of transformations, because it'll help me not to lose what's happening. But there is a specific order when you're doing it on Pearson that I will give you after we do some points. because I think this one's also a good example of why we don't like to just stick with plotting points, as you will see here in a minute. I'm going to do the same 5 points I've done the entire time, -2, -1, 0, 1, and 2. So I will have 3 to the 2 plus 2 plus 3, 3 to the 4th plus 3. That gives me 84. So it gets large quickly. Like, I'm not even going to graph that. Obviously, I didn't make 84 tick marks, even if I'm going by 2s, which I noted I am. I don't want to do 41 or 42 tick marks. No, thank you. So that's why we're going to use our transformations when it comes to graphing in Pearson. So 3 to the -1 would be 1 plus 2 plus 3, which is 3 to the 3rd plus 3, which is 27 plus 3, which is 30. All right, I did do 30 tick marks, so I can do that. So at -1, we're at 30. Now, I only did 15 tick marks because each tick mark counts for 2 on the y-axis. 3 to the 0, well, notice that the only thing that gets the 0 is up here where the negative x is. So that's 0 plus 2 plus 3. So this time we're not going to get out a 1 because we have the shift that happens. We have this horizontal shift, which affects it. So we have 9 plus 3, which is 12. So 2, 4, 6, 8, 10, 12. Three to the -1 plus 2 plus 3 is 3 to the 1st plus 3, which is 6. 2, 4, 6. And 3 to the -2 plus 2 plus 3. Well, -2 plus 2, that's 0. So that'll give me 1 plus 3. Be careful there that you're not tempted, which is 4, to say that that's 0. Now, one thing I do want to point out, we had a vertical shift that happened, right? The vertical shift shifted everything up 3 units. That's including our graph, but also our asymptote. Our asymptote starts at 0, so then our asymptote moves up to 3. So if I were to keep finding values out here, like what is f of 3 and f of 4 and f of 5, you're going to find that it doesn't hug 0. It's going to hug y equals 3. So just note that. You don't have to draw asymptotes on Pearson, but it is something to be aware of because we did do that vertical shift, that affects our asymptote as well and where our graph is going to hug. Questions, comments on any of this? Okay, one of the reasons why graphing by plotting points is nice is because we don't have to worry about the order of our transformations. But when you're in Pearson, the order that you do your transformations will determine if you have a correct graph or an incorrect graph. So this is something you need to write down because it's not in here. I'm going to put it over here to the side. You need to do your transformations in this order. The first thing you're going to do is you're going to do your horizontal shifts. The next thing you're going to do is you're going to do reflections. You can do them both here at this time. So if you have a double reflection where you reflect over the y-axis and the x-axis, that's fine. It doesn't matter which of those you do first. And then the last one you're going to do is you're going to do your vertical shift. If you do them in any other order than this on the Pearson graphs, you're going to get it wrong. It's one of the stupid things about Pearson, because really it shouldn't be wrong, but it does make it wrong. Questions on the graphing part? Okay, the last thing, which is the last thing in the notes, but it's actually the first thing that pops up in the homework, It's talking about this natural base E. So there is a base E. It's an irrational number, and it's 2.718, blah, 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 blah. Irrational numbers do not repeat, and they go on forever. Pi is the most commonly known irrational number. But E is another irrational number, and we will use it, especially when we start playing around in 5.3 in future sections. But we can have a natural base E. We can have an exponential function that looks like f of x equals e to the x. This is known as our natural exponential function. And you can actually compute this using your calculator. You will not be graphing with this, because if that's your base and then you're raising that to exponential powers, that's going to suck. You can't graph with it. Or at least we don't paper and pencil graph with it. You can find graphs on Pearson because you can apply the transformations of the function and not actually do the computations. But your first homework problems are actually things like this, where it says compute f of x equals e squared. And it'll tell you to round to 4 decimal places. That's your first homework problem. So on your calculator, depending on what style you have, you will probably have like an LN and a log button somewhere on here. Usually connected with the LN button or close to it is an e to the x button. And so on this calculator, I have to push second LN, which gives me an E caret and then a parenthesis. So now I can put in whatever power I want, and it's going to tell me what that is. And then I simply type this into Pearson to 4 decimal places or whatever they tell me. That's all you're doing on these problems, nothing else. You will do a lot more with E in the next sections, but knowing what E is helpful. Are there any questions?